In this video, I'm going to walk you through the top 15 AWS services that are the core building blocks of many applications in the cloud. Now, whether you're a complete beginner or you're someone in tech looking to transition your skills to the cloud, I've got you covered. And I'm going to show you some demos along the way as well, so you can see these services in action. Now, on AWS, there's well over 200 services. So there's many services that, of course, I'm not going to cover. I'm just going to cover the core 15 that I see as being the building blocks of many applications in the cloud. Now, if there's other services you're particularly interested in, please comment and let me know, and I may well create a future video. Now, we'll get straight into the content, but if you want to see more videos like this, please make sure you like the video, subscribe to our channel, and hit that notification bell. Now, the first service I'm going to cover is the Amazon Elastic Compute Cloud, EC2. So EC2 is basically instances which are virtual servers running in the cloud. So think of this as a server which is running an operating system, and that operating system can be Linux, it can be Windows. In fact, there is an option for Mac OS as well. So instances are virtual servers. Now, for those of you who are familiar with virtualization, services like VMware or Xen Hypervisor or Microsoft Hyper-V, you know that a virtual server runs on a physical server. So in the AWS data center, there are physical servers. Now, AWS manages those. Those are known as the EC2 hosts. So on top of that, we then have the virtual servers. That's what you get to manage. Now, the virtual servers are where you have your operating system, so you can choose which operating system you want. And they have a certain amount of virtual hardware assigned to them. And of course, there are different options there. We call them instance types in the cloud. So you can select how much CPU, how much RAM, how much memory, what type of network bandwidth you actually need. So the key here is that AWS is managing the data center, they're managing the physical servers, they're managing and creating the sort of layer of virtualization. And then all you need to do is just actually go and launch your virtual servers and choose the various different options in terms of how much hardware you want, what operating system you need, etc. So let's go to AWS. I'm going to show you how to actually launch a virtual server, an EC2 instance in the cloud. So here we're logged into AWS, and what you'll see is there's a big menu here of services. There's literally over 200 services. I haven't counted them for a while, but there's a lot of services here. And so we have all sorts of different categories. Under compute, we'll see EC2, and I've put a star on there, so I actually have it as a shortcut because obviously you use this service quite a lot. Now, EC2 is actually also the building block of many other services. So for example, database services like the Relational Database Service, RDS, which runs SQL Server or MySQL, that service runs on EC2 instances as well. Many others do also. So here on the EC2 dashboard, I can click Launch Instance, give it a name if I want to. I can choose the operating system now. So we call this an Amazon machine image that you're actually choosing, which is essentially the operating system and some other settings for what you're going to launch. So here you can see we've got Linux, we've got Mac OS, we've got various different Linux like Ubuntu, we've got Windows here as well. So I'm going to leave the default and just boot up a Linux instance. And here I can choose my instance type. So this obviously determines how much I'm going to pay. So you've got to be very careful here because you can go to some very expensive instance types with huge amounts of hardware. What I normally do is just use this T2 Micro for demo purposes because it only has one virtual CPU, 1 GB of memory, so it's actually in the free tier. AWS does have a very generous free tier, so you can do a lot. You can learn AWS and actually practice in the free tier most of the time. So what I'm going to do, I'm just going to leave most of the defaults here. Security groups, basically a firewall. We've got some storage options. I actually don't need to configure anything else. I can literally just launch this instance, and that's it. I will now have an operating system running in the cloud. So if I go back up here to instances, we can see I have a running instance. And once this is booted up, I'll actually be able to connect to it using the command line, using this option up here, connect. So we'll come back to that in a moment. Now, AWS has a few different ways that you can work with it. I'm showing you here the console. There's also the SDK, so the software development kit options for various different programming frameworks. And that means that developers can actually write the code and work with make the API calls basically through the SDK. The API calls are basically the requests to actually do something on AWS. Now, another way is using the command line. So we have this service here called Cloud Shell. I'm just going to open up Cloud Shell in another window. Now, Cloud Shell is basically just a Linux command line in the cloud and actually already has credentials. So I'm already authenticated. That means that because I'm already logged in and I use Cloud Shell, when I make requests through the command line here using the AWS command line interface, I've already been authorized and authenticated to do whatever I'm allowed to through my user account. Now, what I'm going to do here is I'm going to run this command. Now, this is using the AWS command line interface, the AWS CLI, and the command is AWS EC2 run instances, and I'm supplying the absolute minimum information that I need to. The image ID, that's basically determining the operating system. I showed you that a moment ago. And then the instance type, which is going to be a T2 micro. So now with one command, just by running that, it's now going to actually launch a second instance. So if I come back here and refresh, we now have 2 running instances. So that's EC2, really powerful and very important to understand EC2. Now you may be saying, okay, Neil, that's fun, but EC2 is servers and servers are a bit old school. Like maybe I want to deploy microservices architectures. Well, here we've got AWS Lambda. So Lambda is a serverless service. So if you want to move away from managing operating systems, as you have to do if you're using EC2, then you can move across to Lambda, as long as your code doesn't need to run for more than 15 minutes. So in other words, a single execution of your code, if you have an application that's processing data, a single execution of that code cannot exceed 15 minutes with Lambda. Other than that, as long as you're supported frameworks and memory requirements, etc., we can run a lot of services on Lambda. So what is Lambda? Lambda is a serverless service. That means there's no servers to manage. Basically, the server is fully managed by AWS because there's always going to be a server underneath. But in this case, we're going up a layer. So AWS is managing more for us and just providing us a function. Now, a function is essentially where we've gone into Lambda, we create something, it's called a function, and that function is where we upload our code. The code can be from many different application programming frameworks. And once we've uploaded our code to Lambda, Lambda will be executed based on specific events that happen. So the function is invoked. Invoked means something has triggered it. Now, that could be a schedule, so a specific time, or it can be, which usually it is, an API call coming in from another service, which is basically saying, I've got some data, I want you to process that data. So when that happens, the code is executed. Now, with Lambda, you're paying for what you use, as you are with most AWS services. And in this case, you're only ever paying when the code is running. So how long does the code run for? Maybe a few milliseconds, for example. That's how much you pay. You pay according to the amount of time it runs and the amount of memory that's assigned to it. So how much resource it's actually using in the cloud. So perhaps in a real world scenario, what would happen is an application component would be sending some data to Lambda to process. So maybe you have an order system and the order system has received an order and then it's passing it to Lambda. Lambda is going to process that order and then store the information somewhere or pass it to another application component. In the case of the diagram here, the data is being written to a DynamoDB table. So let's have a look at Lambda in action. So if I come back to the console, now I'm going to open up Lambda, and in the Lambda console, I'll create a new function, and we'll just call this one Python test. Now here we can see the runtime. So these are the application frameworks that are supported on AWS Lambda. And I'm just going to choose Python 3.13. I'm not going to make any other changes at this point. I'm just going to create the function. Now, once you've created your function, you then need to add some code. By default, Lambda is going to add some very simple kind of hello world code to the function. So here we can see the code that was added by default. It simply prints out hello from Lambda. Now, there's a few different ways we can invoke this function to test it. And one is literally using this test function here. I'll actually go over to the test pane. And what we'll do is we'll create a new test event. I will just call it test. I will save that and then run test. And what happens is we can see that the function executed, it printed out the hello from Lambda message. And then we can see some information about how long it took to actually execute. Here we go, 20 milliseconds, and how much memory was utilized for that execution. 128 megabytes is actually assigned to the function, so we'll be charged accordingly. So that's a very simple demo of AWS Lambda. We will come back to Lambda a bit later on. I'll show you a more interesting example of using Lambda in a serverless event-driven architecture. So next up, I want to cover Amazon Elastic Container Service, ECS. So this is where you can run Docker containers on AWS. With ECS, we create a cluster, then we create tasks. Tasks are essentially running Docker containers, so just slightly different terminology on AWS. And we create those containers, those tasks, from a task definition, which is where we specify the settings for the container. Then we can also store images in the Elastic Container Registry. So that's another service AWS provides for private repositories for storing your Docker images, or you can pull straight from Docker Hub. Now with ECS, we actually have container instances. These are EC2 instances on which we can run these tasks. Now we do have to manage those. However, there's another option for ECS called AWS Fargate, which is completely serverless. So you're just running Docker containers with no service to manage whatsoever. Now let's have a look at some storage options on AWS. Now, first, a quick concept that you need to know, block storage. So block storage is typically where we have hard disk drives or solid state drives, and they're usually physically attached to a computer. So hard disk drives are block-based storage systems. Now, with a block-based storage system, this is where you can actually store your operating system. And we can partition and format. So if we had a Windows operating system, for example, you might have a C and a D drive. So we've partitioned the physical drive. That's what you can do with block storage, as well as installing the operating system itself. Now, for block-based storage on AWS, we have the Amazon Elastic Block Store. With EBS, the volumes that you attach to your instances are actually attached over a network connection. However, they are using block storage protocols. So we can see here we have the EBS volumes, and we can connect those to our EC2 instances. If you're wondering what these icons are in the host server here, these represent instance store volumes, which are another type of block-based storage that is physically attached in the host server itself and very, very high performance. With the EBS volumes, they're also high performance. So you can actually tailor the performance you need based on the settings that you define when you create the volume. And the underlying systems are hard disk drives or solid state drives for EBS volumes. Coming back over to the AWS console, I have two running instances here. Now, if we go across to this storage tab, we can actually see here the EBS volumes that are attached. So here we have a volume. Now, if I go down on the left-hand side here to the Elastic Block Store, volumes, here we can see the volumes as well. And I can create new volumes, and I can choose which type of volume I want. Do I want an old-fashioned magnetic standard, which is a hard disk drive, or a throughput-optimized HDD, or a cold HDD? These are lower performance. They're good for throughput in some cases, but general purpose SSD is obviously a solid state drive option, as is the GPT-2 and 3, and also these ones, these IOPS SSDs, where you actually get to define how many IOPS you want. So that's IOPS is input output per second. It's essentially the performance of the solid state drive. If you're wondering how you back up these drives, then what we can do is we can create something called a snapshot, and that is a point in time copy of this particular volume. So that's the way that we can back up EBS. Now, another type of storage that's very, very popular in AWS is the Amazon Simple Storage Service, S3. Now, S3 is an object-based storage system. With S3, we create what's called a bucket, and then in that bucket, we store objects. What are objects? Objects are basically just files. So Word documents, PDFs, MP4s, JPEGs, whatever type of file you have, log files, could be pretty much any type of file. So we store objects in the bucket. Now, why are we referring to them as objects? And what exactly does object storage mean, and how does it differ from file-based storage, for example? Well, with object-based storage, this is essentially API-driven. So every file operation that you perform, uploading, downloading, deleting files in an S3 bucket, can be performed using an API call. That is really powerful because it means that developers with very simple amounts of code can actually upload and download files from an S3 bucket. So literally just a few lines of code. So with object-based storage, we're able to access it programmatically using the Hypertext Transfer Protocol, HTTP. So of course that means it's very good on the internet, and a REST API. That's the type of API that we're using here. Let's have a look at S3 in action. So I'm going to open up the S3 dashboard here, and I'm going to create a bucket. So let's just create a bucket, and I'm going to call it my test bucket. And then I'm going to add a bunch of random letters and characters to make sure that it's unique, because I guarantee you somebody already has a bucket called my test bucket, and it does need to be unique. So I'll ignore all of the options here. There's encryption options. There's all sorts of different security settings we can apply, but I'm just going to create the bucket. So now I have my test bucket, and let's just copy the name of that bucket. And what I'm going to do is I'll show you on the command line how easily we can actually work with files with S3. So what I'll do here is I'm going to create a file called testfile.txt. And what I'll do then is I'm simply going to copy it. So I'm going to run the AWS S3 cp, that's copy, testfile.txt, and then I'm going to copy it to the destination, which is going to be my S3 bucket. So now that's been uploaded, if I come back to the console here and go into my bucket, there we have the test file. And then, of course, I can, if I just remove test file from my computer here, so or from the Cloud Shell rather, then if I run ls, it's gone. And now I can do the reverse, which is just s3 cp s3 / bucket name / testfile.txt. And then we're going to put that back here on the file system, and it's back again. So super easy from the command line, and very easy as well using one of the SDKs if you want to do it in your code if you're programmatically calling S3. So a lot of applications will use S3 for storage because it's so easy to use using an API, and because it's very good over the internet as well, which is great from a latency perspective, depending where your application is and your actual data itself. Let's move on to networking, and I'm going to cover here the Amazon Virtual Private Cloud VPC. With VPC, we create a virtual private cloud in AWS, and that is essentially an environment in which we can launch our resources like EC2 instances, and it's actually private. We can choose whether we want to allow public accessibility to it or not, but that's completely up to us. And we get to define the networking ranges, the IP address ranges that we're going to use within our VPC. So it's our own private networking environment within AWS. We can create private subnets, which are only accessible within the VPC, unless we set up specific routes and connections outside of the VPC, and then public subnets, where we might launch public-facing resources like websites or load balancers. Subnets are created within availability zones, and availability zones are basically data centers. So AWS has lots of different regions around the world, and each of those regions will have multiple availability zones, so we can launch our resources across different AZs for redundancy purposes. Now, an internet gateway will attach to the internet, and within the VPC, there's actually a router which routes traffic in and out of the VPC and within it as well. And we get to control that router using a route table. So that defines the routes that we want to actually allow. Now, within our VPC, as I mentioned before, we get to choose the ranges of IP addresses, the classless interdomain routing CIDR address blocks. And we can then subdivide those address blocks to create all of our different subnets within the VPC. So each VPC may have a different block of IP addresses. It's not required. You can have overlapping IP addresses depending on how you need to interconnect those VPCs, if at all. So you can create multiple VPCs within a region and set up the IP ranges as you need them in your company to suit your particular requirements. Each subnet will then have a block of IP addresses from the overall CIDR block that's assigned to the VPC. Coming back to AWS, let's open up the Virtual Private Cloud Console. And within the Virtual Private Cloud Console, every region, so you can see these are all the different regions that are available currently on AWS. So I'm in North Virginia, that's called US East 1. And every region will have a VPC, what's called a default VPC, enabled by default. So that's already been created. But I can then go and create my own. If we have a look at subnets, there are several subnets within the default VPC. We can look at the route table here, and we can actually see what routes have been defined. In this case, an internal route for routing within the VPC, and then an external route going via an internet gateway. Now, if I want to create my own VPCs, I can just come up here, choose VPC only, or this thing called VPC and more. VPC and more basically shows me a sort of picture here of what I'm creating, and it gives me some settings. So it's super easy to actually define a VPC and create it. For example here, I just give this a name, just call it my test VPC. I can change the CIDR block if I wish to. I can change the number of AZs, public subnets, private subnets, etc. I'll just turn off that setting to make this nice and quick, and then create the VPC, and you'll see how fast this is. It's literally just creating this in less than 30 seconds. So now I have a completely new VPC, and if I wish to, I can now launch resources into this VPC, which has its own subnets. If I just click on refresh here, we can see the subnets that have been created for that VPC. So that's VPC. Now, another really important service is elastic load balancing. Now, when we run our applications in the cloud, we might launch applications across multiple availability zones for resilience. And we also want to be able to scale. Maybe we don't just want one instance of the application running in each AZ. What if we get a lot of traffic coming to our particular application? We want to be able to automatically scale that and launch lots of instances. Now, when we do that, how are we going to direct the traffic directly to each of those instances and make sure that we have it being distributed evenly? Well, that's where we launch the Elastic Load Balancer. So now when users connect, they're connecting essentially to the endpoint of the load balancer. That's one network address. And the load balancer takes care of making sure that it sends the connections to different instances. If an instance fails, then the connection will just get rerouted to a different instance. So here, user 1 was then reconnected from the failed instance to instance 4. ELB would then take the instance out of service, and we can use a service called EC2 Autoscaling to now automatically replace the instance. Autoscaling also is the service which we can use to scale based on performance. So we can say, well, if the application reaches about 80% utilization in terms of CPU power, then we want to launch more instances. And likewise, let's save some money when it's not being utilized and terminate some instances as well. So now we have a new instance. Users can be load balanced to that new instance. Now we'll come back to load balancing in a minute. I will do a demo on load balancing, but I'm going to use CloudFormation for deployment. So what is CloudFormation? So if you're familiar with Terraform, it's basically the same thing, but it's AWS. So the scope of CloudFormation is deploying resources on AWS using infrastructure as code. That means the infrastructure pattern, so what we want to build, is defined in a template using code like this in either YAML or JSON. We pass the template file, which is where we've got this code, to CloudFormation, and it's going to go and actually build the infrastructure. So whatever we've defined in the template is now going to be built. For instance, here are VPC, subnets, autoscaling, load balancing. So CloudFormation is a really useful service, especially if you're deploying mainly AWS resources. It doesn't have support for third-party resources or other clouds like Terraform does. Now let's go and see CloudFormation in action. So I'm going to open up CloudFormation. In CloudFormation, we create something called a stack. And what I'm going to do is upload a template file. So I already have one, which is on my desktop here. And this one is actually going to deploy a load balanced environment with autoscaling, load balancing, EC2 instances, and a simple website. So I'm going to give it a name, just call it my stack. And I need to add an image ID. So that's the Amazon machine image, the type of instance I want to launch. So in this case, it's going to be a Linux-based instance. And then I can choose the instance type. I'm going to choose one of my VPCs. I'll choose the default VPC. And then I'm going to choose a couple of different subnets. I'm going to choose 2 different subnets within that VPC because I want to make sure this is a resilient infrastructure. Click on Next. I'm going to just ignore all of the other options for now and then submit. Now what happens now is it's going to take that template file and it's going to start building the infrastructure. And we can actually see that happening here. You can actually see the template as well. So this is the actual template that I just uploaded to CloudFormation. So what we'll do now is we'll just watch and make sure that all of this works. And it will take a few minutes. I'm just going to pause while that happens. And once it's complete, we'll go and have a look at what's been built. My stack is now complete, so just took a few minutes to get here. And if I go across to EC2, we can now see I've got 4 running instances. So a couple of new instances have been launched. Now, if I come down to load balancing here and load balancers, this is my load balancer. And it has a DNS name, so I can now actually test that this is working. I'll just copy that DNS name into my browser. And here we've hit one of the instances, and the website on this instance has been configured to basically display a message that tells us which availability zone it's in. So this one is in US East 1C. That's one of the data centers that AWS has within that region. And if I refresh the page, which I'm doing now, we can see it's changing from A to C. And that's where we're actually load balancing between the instances in those 2 different AZs. So that is load balancing. And by the way, load balancing in this case has been launched through CloudFormation with an auto-scaling group. The auto-scaling group is set to 2. That's the desired capacity. So how many instances do we want running at any one time? We can change that, or we can use automatic scaling where we can define things like how much CPU utilization we want to see before we launch new instances, and auto-scaling then takes care of that for us. So that is elastic load balancing. The next service I'm going to cover, Amazon Route 53. So Route 53 is basically an intelligent DNS service, so a domain name system service. We have a few different features with Route 53. We've got domain registration, so you can register your domains here and they're quite cost effective. We then got the hosted zone, so that is the DNS zone for the domains that we have within Route 53, where we get to define the records. We've got health checks, so it can automatically health check instances to see if they're working or not, and load balancers as well, just to see if they're actually healthy and responding. And then based on that, it can determine what happens. For example, if a load balancer is failing within one region and not returning the health check successfully, then Route 53 can intelligently fail over to another load balancer. So we can set up various different types of policy within Route 53. And traffic flow is a way of automating a lot of that as well. So let's go back to AWS, and I'm going to open up the Route 53 console. And within Route 53, I already have a hosted zone. So I registered this dctaws.com domain name within AWS using Route 53. And within this zone, I can then create my records. So for example, I could create a record, and I'm going to create one for my load balancer. So I can choose an alias to an application load balancer. I can choose the region, which is US East 1, and then I can select my load balancer. Now here are the routing policies. We've got simple, we've got weighted, we've got geolocation, latency, failover. So for example, latency would be if the client is in a different part of the world and there's a region that's closer to them, and you've put an endpoint of your application, essentially a copy of your application in that region, it's going to route them to the lowest latency endpoint. So that can be really good for performance for your customers. Now we'll leave it on simple in this case and just create that record. What happens now, it's created the record. It's a simple A record that will mean that we can now use this domain name, dctaws.com, to connect to my load balancer. Now I've just got to wait to make sure that DNS propagates that change. So once I can see the status changing here, then I can go and actually do the test. Okay, it says it's in sync. So what I'm going to do is open up a new browser window. And what I'm typing in here is dctaws.com rather than the DNS name that we saw before that AWS Elastic Load Balancing gave us. And now I'm able to use that public domain name to connect to my application. So that's Route 53. When we're building applications in the cloud, there are a few different services we can use for integrating those applications. One of them is known as the Simple Queue service. Now, the purpose of Simple Queue service is to avoid direct integrations like this one here. So with a direct integration, what happens is the web tier, in this case, is passing requests straight through to the app tier. Now, what if the web tier suddenly has a huge amount of requests that's too much for the app tier to actually handle? In that case, you have a problem, and maybe it's going to fail. So what we do instead is we put a queue in the middle. The queue now is a place where the web tier can place the information, the messages that contain the data that needs to be processed. The app tier will then poll the queue, find the messages, and process them. and they can stay in the queue for a while. So it's not super urgent, and that means that we now have some resilience. So this is what we call a decoupled integration, and SQS is a great service for this. Now we'll come back and see an example of this in action shortly. Another service for application integration is the simple notification services. This is more of a publisher-subscriber model. So with SNS, we have what's called a topic, and then we have our subscribers. They subscribe to the topic, and then messages can be sent out to all of the subscribers simultaneously. So one message might go to multiple subscribers. That's SNS. So this is also another example of decoupling. Now let's have a look at some database services. So here, the relational database service. This is a managed relational database service. It's used for online transaction processing, OLTP use cases, and it runs on EC2 instances, as I mentioned earlier. So when you launch RDS, you choose the database instance type. Now we have a few different options for the engine that we choose. We can choose the Amazon Aurora, that's the AWS proprietary database service for RDS. Otherwise, we get to choose Microsoft SQL Server, MySQL, and several others as well. The database instance can contain multiple user-created databases as well. So you have an instance, and then you can create multiple databases within it. EBS is used for the actual storage in this case, because remember, this is running on EC2. And that means also that snapshots are the mechanism for backing up these databases, or it's one of the mechanisms anyway. Now let's have a look at DynamoDB. So DynamoDB is a non-relational database. So it's a fully managed NoSQL database service. It's fully serverless. It's a key value store or a document store. It provides very low latency access to your data in the milliseconds. And it offers what's called push button down scaling with no downtime. So you can change the amount of performance that you need without actually taking the database down, which you can't do, by the way, with RDS. So here, the actual data is getting written across multiple partitions, and they're replicated across multiple availability zones within a region. So very high durability as well. The core components of DynamoDB are, we have the table itself. So we create a table. Within that table, we store items. This is the information, essentially the rows in the database. And each of the items has attributes. So remember, this is a key value store. So we have the key, which is the item name, what's known as the partition key, which is the first part there, the user ID in this case. And then we have the various different attributes. So what is the data that's associated with that particular item? Now let's go back over to AWS. We've got a fun demo to do here. So I already created this Lambda function earlier. This Lambda function, what it's going to do, it's going to be triggered by messages that are added to an SQS queue, and it's going to process the data and store the results in a DynamoDB table. So I've created this already. I've added the relevant permissions, which is always required with Lambda to make sure it has permissions to the relevant resources. So we can see the various different permissions that are assigned to its execution role. Then I have a queue. So with the queue, what I've done is I've created a Lambda trigger. That means that whenever a message is added to the queue, Lambda is going to be triggered, and the information in the queue, the message, is going to be sent through to the Lambda function to process. It's going to then process that data, store the results in a DynamoDB table. So that's what we need to create. I've got the DynamoDB console open. I'm just going to create a table, and the name of the table is going to be product visits, and then the partition key is product visit key. That's all I need to enter at this point to create my table. Really fast creating a table, like most things in AWS, in this case, literally seconds. And there we go. It's done. It's active. So the application is now set up, and all I need to do is add messages to the queue. And I'm going to do that using AWS Cloud Shell. In Cloud Shell, I have a directory here. And in that directory, I have these files. Now, if I have a look at one of these files, basically it's just some order information. So it's a fictitious order that we're actually going to add to our DynamoDB table. Now, all I need to do to actually add one of these messages to the queue is run this command. So AWS SQS send message, specify the URL of the queue, and then specify what the data is that we want to send. So that's going to be added now as a message to the queue. Now, if we went to look in the queue, it would be gone instantly. So you can't actually see that sometimes in real time. But what we can do is now explore items in our table, and we can see that we have one item here. Okay, so it's added this fictitious order to our database. And then I can just add perhaps the second one, do the same thing, come back here, I'm going to refresh, and now we have two different orders added to our table. You can see how easy it is to set up a simple event-driven application. So an event happens and then that triggers other actions. And in this case, we've gone from adding the message to the queue through to storing the data in the table. So that is DynamoDB, SQS, and Lambda working together. Now, another really important service is the AWS Identity and Access Management Service, AWS IAM. IAM is where we can actually create users. We can create something called a role, which is where essentially applications or individuals can then assume this role and impersonate or take on a certain identity with certain permissions assigned. Federated users, so they might come from external identity providers such as Google, Amazon, or Facebook, and then applications as well, which need to authenticate and gain access to AWS. So these are the principles. They get authenticated so that they can then send requests using API calls to AWS. So with IAM, we then have policies. We can use identity-based policies or resource-based policies. I go into that in a lot of detail in my training, but these are essentially defining what people are going to be authorized to do once they are authenticated. So what are we allowing? What are we denying? And then the API calls can go through to the relevant services. For instance, being allowed to launch instances, get some bucket information, or create a user in IAM itself. So actions are then authorized on AWS resources. Coming back over to AWS, if we go to the IAM service, we can see here we have users. I've just got one user in this demo account. We've got roles. We've got policies that we can define. These are the permissions. They're all written, by the way, in JSON. So we can define them in code, and then that applies the various permissions. And we have user groups. So I have a group called admins with a permissions policy assigned to it, allowing me all the privileges I need for this demo account. So that's IAM. Now, the last service I'm going to cover is Amazon CloudWatch. This is used for performance monitoring, alarms, log collection, and automated actions as well. So we can use it to collect performance metrics from AWS systems and on-premises systems as well. And it automates responses to operational changes. If we want to configure it that way, it can help us to improve operational performance, resource optimization, and also derive insights that we might want to take actions on from log files in CloudWatch. And of course, we get operational visibility and insights into what's happening in our applications, especially around performance. We always want to know, how are they performing? We might want to be able to anticipate something that might go wrong, for example, ahead of it actually happening. So let's go to CloudWatch. Here we can see alarms. So I don't have any alarms at this point. We've got log groups. So for example, here, lots of Lambda functions that I've created in this demo account. We can see the log groups there. So it's storing various information in a log stream about every invocation of those Lambda functions. We've then got the metrics. So you can explore the metrics for different services. For example, let's choose EC2. And in EC2 here, we can see some information. What's happening with our resources? What is the CPU utilization? What about the disk utilization? What about the network? Are the status checks passing so we know that it's a healthy instance? So lots and lots of information. You can create custom dashboards as well in Amazon CloudWatch. So that's it for this video. Now, if you want to get trained on AWS to become a cloud engineer, a cloud architect, a DevOps engineer, or a cloud AI engineer, we have a bootcamp pathway specifically for you. It's really, really hands-on, where you're going to get taught to really build applications, collaborate with other people, work in teams, and so on. Now, check the description of the video if you're interested in becoming an expert on AWS and working in this industry.